The shape of a molecule is very important in terms of how it works. In this first example, sucralose, Splenda, has a similar shape to sucrose, so our taste buds sense both of those as sweet. Sucralose, however, has chlorine atoms, so our digestive system cannot process it. This makes it a 0-calorie sweetener. In this second example, naloxone is given as an antidote for a heroin overdose. Their similar but not identical shapes mean that they target the same biological receptors but have different biological effects. Valence shell electron pair repulsion theory, VSEPR, pronounced Vesper, is the simplest theory to explain why molecules have the shapes observed by experiment. The idea is that electrons, being negative, repel each other so that electrons are as far apart as possible in a molecule. We will talk about electrons in terms of electron domains, which can be bonds, single, double, or triple, or lone pairs. For example, a central atom with 3 single bonds has the same number of electron domains as a central atom with 2 single bonds and a double bond, or as a central atom with 2 single bonds and a lone pair. In each case, there are 3 electron domains. So let's take a look at the basic shapes, shapes with no lone pairs. If an atom has 2 clumps of electrons, electron domains, the shape is linear. Take a look at the rest of the chart to see the names. We can see how the shapes resemble geometric shapes, so we refer to this as molecular geometry. In this class, we will focus on linear, trigonal, planar, and tetrahedral. One note, we can describe the structure as tetrahedral, an adjective, or as a tetrahedron, the noun. This is true for all the shapes. So here is how we determine the shape. First, we need to draw the correct Lewis structure. I did that for you already. Next, we need to determine the number of electron domains. Use the number of electron domains to determine the structure. So I will show you the first 2. Carbon has 3 electron domains, here, here, and here. 3 electron domains make a trigonal planar shape. In the second example, we don't really have a central atom, but we know that the 2 points define a line, so CO must be linear. Pause the video and try the next 2. So both of these turn out to be tetrahedral. It is a very common shape in organic molecules. You saw in the PhET activity that lone pairs affect the shape. Let's take a look at how. To determine the shape of a molecule, we start like we did before, but now we need to look at the number of lone pairs to determine the shape. For example, SO2 has 3 electron domains, but one of those is invisible, so the shape is bent. You should have also seen in the PhET activity that the angles for some of the molecules are smaller than others. This is because evidence shows that a lone pair takes up more space than a bonded pair of electrons. So you can see the bigger lone pair smooshes the atoms closer together. So you can see that the 109.5 degree angle of a tetrahedral molecule is squished a little smaller in ammonia and even smaller in water. And we call the shapes of the molecules trigonal pyramidal, and bent. So let's look at how we use this chart. Steric number is another way of saying electron domains. E is the central atom, the one we're finding the shape for. X is all other atoms, and the pair of dots is a lone pair. First, we figure out the number of electron domains. Then follow that row across until we find the number of lone pairs. This gives us the name. I will go through the top row, then I'll let you try the bottom row. For CS2, carbon has 2 electron domains, so the only choice is linear. The chlorite ion has the Lewis dot structure shown here. We have 4 electron domains, so we'll start on this row. We also have 2 lone pairs of electrons, so it is bent. The third one, the chlorate ion, also has 4 electron domains, but it only has 1 lone pair. Following the chart, it is trigonal pyramidal. That's all there is to it. You will always have the chart on any assessments, so your goal is to be able to use the chart. Now pause the video and give it a try. For methanol, you will need to look at the molecular shape around carbon and the molecular shape around oxygen separately. Okay, let's look at the results. Nitrite has 3 electron domains and 1 lone pair, also bent, but with a larger bond angle than chlorite. Sulfite has 3 electron domains, no lone pair, and is trigonal planar. Carbon and oxygen each have 4 electron domains, but carbon has no lone pair. It is tetrahedral. Oxygen has 2 lone pair, so it is bent, with a bond angle a little less than 109.5 degrees. Now let's take a look at the models of the shapes. We can see that the 3-dimensional models, based on experimentally determined calculations, reflect what we came up with using VSEPR. Well, that's it. I hope it helped.